What's up, guys? New video, new topic, looking at redox this topic. And we're going to start off by looking at oxidation states. Before we get into it though, please like, subscribe, share, getting even closer to that 100 subscribers mark. Be good to get there so this video can have as wide an impact as possible. Let's get into it. So oxidation state, oxidation numbers sort of talk about movement of electrons and things like that. We'll worry more about that later. For now, we'll look at how we can assign sort of what number that is. So we'll look at some examples and we'll see how we can apply that to rules and stuff. So for starters here, Cu2 plus we say has an oxidation number of +2. Cl minus we say has an oxidation of -1. So if we've got simple ions, as is the case here, so simple ions means ions just by themselves, our charge is our oxidation number. So simple ions, let's make that a bit smaller. Charge equals oxidation number. Next, here example Cl2. Essentially, any element that's by itself has an oxidation number of 0, right? So that we could have Fe, and that would be 0, etc., etc. So elements have an oxidation number equal to 0. Next, so OH minus, good example. So here we've got an example of a polyatomic ion. Here, all of our oxidation numbers will add up to -1, right? And we'll explore that a little bit more later. So polyatomic ions total of oxidation numbers equals charge. And here we know that this O is going to be the negative one, and we know because it's more electronegative. So generally more electronegative equals 0. Next, a few different things here, right? So hydrogen, we can always assume, generally speaking, is going to be +1. There's a few exceptions, but in most cases it's +1. And we can see that this is obeyed here. One carbon is going to be -4 in this case. So we've got 4 of these +1s to balance that out. So we've got our total charge of 0, our total oxidation number of 0. Next, oxygen here, the most electronegative. So you can see here, carbon is more electronegative, so it's negative in this case. Here, in this case, oxygen is the more electronegative, so that is the negative one. Now here, this is our rule. Group 2 is generally going to equal -2. There are going to be exceptions, and I'll give you one exception very quickly. We've got an exception of H2O2, hydrogen peroxide, where hydrogen is +1 and oxygen is only -1. Strange example, but that's an exception to that rule. Next, NaCl. We've got two things there. Na in group 1 equals +1. Chlorine in group 7, generally -1. And last of all, another rule here, group 2 is generally plus 2. So it follows very similar to, well, exactly the same as when we label our ions. It's got plus 1, plus 2. Here's probably going to be plus 3. This is going to depend. Minus 1, minus 2, minus 3, but again, could depend. Best thing for us to do is to look at some examples. But you'll see like there's lots of things we haven't labelled. So this is going to be a case of where we look at things that we're more sure about first and then work from there. So this is a good example of that. Vanadium sits here within our transition metals. It's a super interesting thing where we can have a wide range of oxidation numbers with vanadium, and we'll see that in these examples. So first of all, vanadium in this case is 0, and that's because it's in its elemental state. Next, we've got VO2. Remember, oxygen is in group 6, so it's going to have a minus 2 charge. So we've got 2 lots of these minus 2s. We know the whole thing is going to equal 0, and so therefore we can assume that vanadium is going to be plus 4 in this case. And again, we can sort of think about this in sort of algebraic terms. We'll do the same next. So here, oxygen again is in group 6. Let's change our angle a bit. So we've got 5 lots of minus 2. The whole thing has a charge of 0. And we've got 2x, if you like, 2 lots of vanadium. So there we get to minus 10 divided by the 2 plus 5. Next, V2O4, again we can work it out in the same kind of way. We've got 4 lots of our minus 2. Our whole thing has a charge of 0. And we've got 2 lots of these vanadium. So we've got minus 8 divided by the 2, we get to plus 4 again. Next, VCl3. So in this case, we know chlorine is in group 7. So we've got 3 lots of minus 1 in this case. Our whole thing has a charge of 0. And we've only got 1 lot of vanadium this time. So if this is 3 minus, this must be 3 plus. And the last one, this is interesting because we know that all of this has a charge of 2 minus. Think sulfuric acid. So this whole thing has a charge of 2 minus. We can work it out more individually though. Here, oxygen has a charge of minus 2. Sulfur in this case is going to act quite funnily. It's going to have a charge of plus 6. But anyway, because we know that all of this is 2 minus, we know vanadium must be 2 plus here. Next, I2. So looking at iodine in this case. So iodine here, it's an element in its standard state, so it must be 0. Hi, hydrogen, remember, is generally plus 1. Whole thing equals 0, so iodine must be minus 1. IO minus. So this time we've got a charge on the outside. Remember, oxygen is minus 2. We know our whole thing equals minus 1. Therefore, iodine here must only equal plus 1. I2O7, we've got 7 lots of -2 equals 0 plus 2x. So we've got -14, so here iodine must be +7. Next, I2O3, got 3 lots of -2, whole thing equals 0, 2 lots of x, -6, so each iodine must be +3. Last one, IO3, got 3 lots of -2, the whole thing equals -1, only got one of these, so we've got -6 here, so the iodine must be +5 in this case. So again, I think the moral of this is we look at the things that we're quite sure about. We can generally be very sure about hydrogen and oxygen, and then we work our way around that. What I'd like you to do, give these a go. Work out the oxidation numbers of these, and we'll go over them at the end of next video. For now though, let's go over the answer to the question at the end of last video, so looking at simple intermolecular. So onto this one. Melting point of XCF4 higher than the melting point of PF3. Explain why the melting points are different. So we quickly need to sketch these out, which I've done already. So we've got square planar, we've also got pyramidal. So we should know that both have like polar bonds, but they're not polar molecules. So here, this is symmetrical. So all we have there is van der Waals, whereas this is not symmetrical. So here we have delta positive of the phosphorus, the delta negative of the fluorines. So this will have a dipole-dipole. As well as van der Waals. So that begs the question, why is the melting point of XCF4 higher than PF3? Because we know that this is going to have stronger bonds in terms of the stronger type of intermolecular forces. Well, it's because this is so much of a bigger molecule. So we first of all need to say what type of bonding both have between the molecules. And we then need to say, because XCF4 is a large molecule, the van der Waals are stronger. And then we've got our blanket, so require more energy to overcome the forces between the molecules, therefore higher melting and boiling point. Hope that helps. Again, you know, even if you haven't got this last section, you pick up around 4 marks for all of this stuff. It's that last section you pick up that final mark. Hope that helps. Happy revising, and I'll see you next time when we'll look at redox half equations.